discrete random variables. A random variable is just the outcomes you get when you do some probability, but in number form. So for example, and we normally say, what's the probability of rolling a 6 when you roll a die? We're like, oh, it's 1 out of 6. When we do a random variable, it's more like if I roll the die 5 times, how many times could I get 6? And that's a slightly different question, because now you're saying if you roll die 5 times, how many times can you get 6? Well, you get 6 0 times. 1 time, you get 6 2 times. 3, 4, or if you're really lucky, you get 6 all 5 times. So that would be your possible values. Right? Notice it's not, oh, odds of getting 6. It's saying it's odds of getting 6. How many different ways could you get 6? Well, I could get it 0, 1, 2, 3, 4, 5 times. That's what we're going to be talking about. Right, that's what we're going to talk about. So it's random variable because how many times we get 6 is random. That's kind of the idea. Now there's 2 types. There's a discrete random variable, which we get by counting. So those are just like when things have a certain like value set to them. Like I always say, like shoe sizes. Right, you can only buy it in sizes of 5, like 5.5. 6. You can't get a 5 3/4 shoe or 5 2.7 shoe. So the general rule is if you could count it, then it's discrete. Here's some examples. Number of houses in a suburb, right? You're not going to have with the power state. That's irrelevant. The number of houses in the suburb, you're not going to have 3.5 houses. It's going to be a solid house. Number of bikes sold, right? You're not going to sell 2.15 bikes. You're going to sell 2, 3, 4, 5 bikes. The number of bad light bulbs. Again, you can't have half points on that. So those are called discrete random variables. So if you could count it, they're discrete. The other type of random variable is a continuous random variable. These are values where it's not really countable. How I said shoe sizes, if you actually just measure your feet, if I said like size of feet, well, that could be anything. Your feet could be exactly like 7 inches, but it's probably more like 7.1346. It never like stops growing type of thing. Where like it's not gonna, your feet's not gonna stop growing at like exactly 7 inches or 8 inches or whatever. So when it has like a range it could kind of fall into because it's any values possible, then it's continuous. The shortcut for that is a measure. If you have to measure it, like your feet with like a ruler or something, then it's continuous, most likely. Right? The height of men, same idea. The height of people in general, it's not, they don't fall into certain categories. They kind of fall in between. The volume of water, how much water is in a water tank, right? Again, it's gonna fall kind of in between values. It's not just automatically jump up to the next set. So that's continuous, right? If you have to measure it, if it does like it could be any value in between, then it's continuous. Here's some quick examples. Time it takes students to select at random to register for a fall semester, right? That kid's not gonna finish registering in like 10 minutes. It might be like 10.371, 10.5. It's not gonna be exactly 10 or exactly 11, right? It could fall any value in between. So that's going to be continuous, right? You can measure the time with the stopwatch type of thing. The number of bad checks drawn. See, like bad checks drawn, right? So how many bad checks do we have? You can't have a partial bad check, right? It's either have 2 bad checks or 3 pounds. So you count the number of bad checks if you work at the bank. So it's discrete. The amount of gasoline needed to drive a car 200 miles. If you're driving, you know your odometer doesn't skip values. There's all the in between values and like little decimal point. So that's continuous. The number of traffic fatalities per year in the state of Florida. Well, that's morbid. Now, if that's an average, now that's kind of a tricky one. If that's an average is continuous. If you take an average of stuff, like you think of points per game, like in basketball, it could be like 28.7. Because it's an average, so you can have any value in between. If you're talking about points in a single game, right? If Demuro is playing, then it'd be like 0. But if I was playing, it might be like 12. Right? But again, it can't be, it's a single game, you're not going to have 2.3. He's always sad when he plays basketball. And over here, happy. I'm not sure why I have one eye. It's my sunglasses. I'm cool. Anyway, so that's kind of a weird one. Number of fatalities per year. Per year makes it sound like an average. I'm gonna say continuous, but in general, it's kind of a weird. The distance of golf ball travels. Again, I could fall any value in between, right? It doesn't have to fall at 20 feet and then 21 feet. It could be somewhere in between those 2 feet. You measure it. It's continuous. The number of shits in a Pearl Harbor on any given day, the number of ships, or you can count those. Discrete. You wait before breakfast each morning. Well, again, that could be continuous, could fall any value in between. Just like that. So that's kind of a general idea. Now let's talk about how we display our probability distributions. So here we go. In this problem right here, this is a little example. They're tossing a head twice, so tossing coins twice. So you get heads, heads, right? Or tails, heads, heads, tails, and tails, tails. And what we're checking here is number of heads you get. So like they're going to say, let X be the number of heads you get when you flip a coin. If you look at it, you have 3 possibilities. You could get, like right here, you get no, right here, sorry, you get no heads, you get both tails. So you have 0. X would be 0, you could get no heads. Or you could get 1 head. This happens 1 out of 4 times, right? You can only get 1 head. That happens twice, right? Heads, tails, tails, heads. So that happens 2 out of 4 times. That's a 1. That happens 2 out of 4 times. Nice save. And then over here, number of heads, you might get it twice. Both times you get heads. So you might get 2 heads, which only happens 1 out of 4 times. So go right again. The number of times you actually hit heads is the random variable. The question is, how many times could you get heads? And it's like, okay, I could get heads 0, 1, or 2. And these are the odds for each one, right? 1 heads happens twice, no heads happens 1 time, and 2 heads happens 1 time. And so if you plot it, you can plot it in a spike graph like this, where you go, here's 0, 1, 2, number of heads, and then you just draw those spike graphs, 1/2, 1/4, 1/2, blah blah blah. Or you could draw in a column graph. Either way, the same. Again, if we're doing continuous data, this would be a connected. It'll be like this if it's continuous. That's my drawing, right? That's how you draw continuous. If it's discrete, you draw it separate. But that's how you draw probability distributions. Let's go for a quick example. The supermarket has 4 checkouts A, B, C, D. The management checks the weighing devices at each checkout. If a weighing device is accurate at Y, a Y was recorded, so it's accurate. So yes, it's accurate. Otherwise, a no is recorded, it's not accurate. The random variable being considered the number of weighing devices which are accurate. So again, we're going to that's a straight line. Believe. So we have 4 things here. Suppose X is the random variable. What's the value of X? So A is just saying, hey, what values could you have for X? Now again, they want X to be the number of weighing devices which are accurate. You have 4 weighing devices, so you could have all 4 of them be accurate, or just 3, or just 2, or just 1, or maybe none of them are accurate. Right? Those are your possible values for X. 0, 1, 2, 3, or 4. Tabulate the possible outcomes and the corresponding values for X. That one we are not going to do because we don't have 2 hours to watch me tabulate outcomes. It'll be something like this. You have A, B, C, D, and then they could all be accurate, or only A is accurate, or maybe the first 2 are accurate. It's gonna be there's gonna be 16 possibilities. So trust me, there's a lot. It's not the biggest deal. You just go through it and then count each one up. Instead, let's go to this because something we're actually gonna do. Describe using the X events that exactly 2 devices being accurate. So remember our possible outcomes right here? Exactly 2 just means X equals 2. You're going to have exactly 2 accurate. That's what happens right there. Compared to this one, at least 2 accurate. Remember, that means like you want at least 2 cookies, 2 or more. Right, so that's X is greater than or equal to 2. So the way you would do this is X equals 2, 3, or 4. Math-wise, we just add these up. Figure out that one, figure out that one, figure out that one, add them up. But that's the general idea. Let's move on to discrete probability distributions. This is all going to be about how to read probability distributions in general, how to do stuff with them. A probability distribution is just like any other distribution, guys. It's like any other probability. There's all this fancy talk. This means, like everything else, you can only go from 0 to 1. Right? The max probability is 1. The least probability is 0. You can never have more than 100%, never less than 0%. And just like before, if you add up all your probabilities, if I give you a whole table of them, it should equal 1, just like always. and all your probabilities describe the probability distribution, which just generally means that they'll give you a formula or a rule to follow to find out all your actual probabilities. That's all that kind of means. There's lots of ways to display a random probability distribution that's discrete. You can do it in table form, you can do it in graph form, they could give you an equation. So lots of ways. We'll see a couple of these ways up here. Key thing to keep in mind when we talk about discrete values, right? Discrete values, they skip a beat, right? Like I said before, they're countable. So you go 3, you go 4, you go 5. It can't be 3.1. It can't be 4.01. It has to be certain values, like just generally the natural numbers, right? So they have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So why is that important? Well, for stuff like this, right? X is equal to 3, 3. Or this is all just more vocab. That'll come up more later in a couple of sections. So probably that X is at most 3, right? So it's more vocab. Or most, you want at most 3 cookies, so no more than 3. So 3 or less, right? Probably that X is more than 3. This stuff is at least 3, but no more than 7. So just general like Algebra 1, pre-algebra, 8th grade, 6th grade, like understanding word sentences in math. So this is an example right here. A magazine store records the number of magazines purchased by its customers in 1 week. 23 purchased 1 magazine, 38 purchased 2, 21 purchased 3, 13 purchased 4, and 5% purchased 4. What's the random variable? So look what they're talking about. So I know what X is. A magazine store records the number of magazines. The number of magazines. That's a random variable. Number of magazines purchased. Right? So you could purchase. So in this case, you could buy, I guess, 0 magazines. You go in there, don't buy a magazine like most people in today's world. Or you could buy 1 magazine, 2 magazines, 3 magazines, 4 magazines, or 5. So 1, 2, 3, 4, 5 are your possibilities. Make a probability table to display the random variable. So all we do is this. It's like a normal table with perfect straight lines. And you go X and P. X is the random variable. P is the probability. So we could have 0, 1, 2, 3, 4, and 5. Right? 23 purchased 1 magazine, so that's 20.23. 38 purchased 2. 21 purchased 3. 13 purchased 4. And 0.5 purchased 5. Actually, if you add all these up, you get 100. So I was wrong. You can't buy 0 magazines. I guess we're only recording people that did buy magazines. So if you add all these up, you get 100. So there's no leftover for 0. So they only record people that actually bought a magazine. So that's my probability table. That's how simple it is. You put the random variable, right? Again, the idea here is how many magazines can you buy? So 1, 2, 3, or 4. And then you write the probability of each one down there. Now they want me to draw using a spike graph. So all we're gonna do is make a little table here. Here's 0. We'll go up to 38. So let's go 0.4, 0.3, 0.2, 0.1. And then at 1, I have 0.23, so look around there-ish. Draw a little spike. That's a spike. 2, 0.38, so up here. Boom. At 3, 0.21, so like around there. Very close to number 1. At 4, 0.13, so like around here. And then at 5.5, so like right here. Right, so the spike graph, you can see it's, look at the tail, positively skewed, right? A lot of people should be buying, not that many people buy books, bought magazines, but a few people brought the thing higher than it should be, so positively skewed. And most likely you'll buy 2 magazines. That's what that kind of means. Now let's see when they give you a formula to do a probability distribution. So right here it says show the following are probability distribution. So notice how they say show. So again, you got to show it. What does that generally mean? Well, find each probability distribution and then add them up. Right, take the sum. Show it equals 1. That's generally what it means. So let's say this works with A here. Probability of x equals x squared plus 1 over 34, and they give us our x's. So all we're going to do is plug it in. Find the probability of 1 plug it in. 1 squared plus 1 over 34. I did it right here because I don't want to waste your time plugging all these in. Same thing with 2 and 3 and 4. Right? Notice again. Notice first that none of them are negative, so we're still good. So if one of them was negative, we couldn't do it. Not a proper distribution. And then now you want to add them all up. 2 plus 5 plus 10 plus 17. And you would get 37 over 34, which equals 1. So it should work out. Again, all your probabilities should equal 1 together. So it is a probability distribution. Now let's look at this B real quick, right? B looks disgusting. It has all this. It's the same idea. You can plug in 0. So 3 over 0, 0.6 to the 0, 0.4 to the 3 minus 0, or just 3. Right, you have that. 3 over 0, we talked about before, that's 3C0, right? You put that in your calculator, we did the binomial expansion. 0.6 to 0 is this 1, 0.4 to the third, put that in your calculator, multiply it all together, you get the number. We'll do the same thing for all of these, and to spare you the time, I just showed the answer they have in the book. Right, so they plugged all these into your calculator, plugged 3C0, 3C1, 3C2, they got this, and then they add up all the percentages, and they got 1. So again, it follows the pattern. It's probability distribution. None of them are negatives. When you add them up, you get 1. That's kind of the idea. Our next example, they want us to find K. So they're telling us it's a probability distribution. I could talk. And they want us to find K. So remember a few rules of these things. First, the obvious one, right? They should go between 0 and 1. None of them should be negative. None of them should be more than 1. And second, when you add them up, when you add up all the probabilities, it should equal 1. That's what we're going to use here. If I add up K plus 2K plus 3K plus K, it should equal 1, because that's all the probability. All this stuff always equals 1. So in this case, I get 1 plus 2 is 3, plus 3 is 6, 7. 7K equals 1, divide by 7. K equals 1/7. And that's the idea. Right, remember, anytime you have a probability distribution, all this should equal 1. Every single time you have a probability distribution, all that should equal 1. Okay, next example. The probabilities of Jason scoring home runs in each game during his baseball career are given to the following table. X number of home runs per game. So again, just keep that in mind, what's going on. So the number of home runs he hits per game. So 0, we don't know. 1 home run per game is 0.3, which is amazing. 2 home runs a game is 0.10. Still ridiculous. It's almost more amazing than hitting 1 home run a game, like 30% of the time. 3 home runs a game, 4 home runs a game, and 5 home runs a game. Right? So first, state the value of P2. So probability of 2. So remember, that's probably he hits 2 home runs in a single game. That's just 0.10008. Or just round it to 36 figs, 0.109. So he has almost 11% chance of hitting 2 home runs in a game. What is the value of A? Explain what this means. So first, let's talk about how we find the value of A. Right? Now remember, it's a probability distribution here. So if we add all these up, because since they're all probabilities, it should equal 1. Do a little math. If you do a little math, add them up, subtract A from it. A plus 0.49 plus equals 1. Subtract that, and I believe you get A equals 0.5488. I know that's true because I got it from the back of the book. Right, so that's A. What does it mean? It means the odds he's going to hit 0 home runs in a game. He has a 50% chance of hitting 0 home runs. That's all it is. So probability he hits 0 home runs. Loser. Home runs. Okay. What's the value of 1, 2, 3 plus 4 plus 5? Well, 2 ways you can do that. Right? You can add up 1 plus 2 plus 3, 4, 5, or you can use a complement. What's the opposite of that? 1 minus probably using no home runs. Right? So there's lots of ways you can do that. You can just add all those up, take it the slow way, or you can do the mathematical way and subtract these from those. And if you get that, you're going to get 2, 1, 6, 4. I don't think that's what that is actually. 4, 5, 1, 2. Actually, I mean 4, 5, 1, 2. Right, so that's the odds of hitting. Oh, so that's right. 1 plus 2 plus 2 plus 4. You could do that if you want, or you just do 1 minus what you're missing, which is 0. So, and I get this. And that's the odds he's going to hit at least one hit, right? That's what that means. 1, 2, 3, 4, 5. So that's at least one hit. One home run, I should say, not hit. Hit would make more sense, but whatever. Not judging, not judging. Draw probability distribution spike graph P against X. So it would be the same thing. You just draw this here. Here will be X. Here will be P. Here's 0. 0 goes like to 58. Then you go 1. That'll go to 33. You go to 2. That goes to 10. 3 is like even less, way less than that. That's almost less than it. It's like small. And 5 and 6, and they almost non-existent. 6 actually doesn't exist. So that's the idea with that. Okay, last two. Find K in the following probability distribution. This is one I tend to like, and I'm tend to like it too. So what they do is they give you this, and they want you to find K. So remember the way this stuff works. You plug this stuff in. Plug in. So plug in 0. Now again, you're plugging in for X, not for K. So it's going to be K 0 plus 1. Plug in 1. So it'll be K 1 plus 1. 2 would be K over 2 plus 1. And 3 would be K over 3 plus 1. Now, so right, we know to plug those in. What's the other thing we know? If I add up all the probabilities, it should equal 1. So all these things I plugged in, add them up, and it has to equal 1. So you're going to get K over 1 plus K over 2 plus K over 2 plus 1 is 3 plus K over 4 equals 1. Now if you want to solve it, the easiest way to solve this thing would be multiply everything by the LCD, which in this case would be 12. And multiply everything by 12, you get 12K plus 6K plus 4K plus 3K equals 12. 10, 25K equals 12. K equals 12 over 25. And that's kind of what you do one of these. Every time you see they want you to find K in the following probability distribution, plug the numbers in, and then don't forget, hey, if I add all these up, it should equal 1. After that's just math. This is some algebra. One last quick example for this lesson. A bag contains 4 red marbles, 2 blue marbles. 2 marbles are randomly selected without replacement. Let X denote the number of red ones selected. So let's talk about that first. Right, I'm choosing 2 marbles, and X number of red ones you select. So look at the possibilities. Generally it should be, well, let's look at it afterwards actually. Let's make our little, if you look at this one, it's a tree diagram. So let's make a tree diagram first. Right, so here's me selecting marbles out of bag. Right, and they're red and blue. So add to the fact here, a little red, a little blue. I can see color is a little red. Anyway, we could select red, or we could select blue. Right, so 4 red, 2 blue, so a total of 6. So 4 out of 6 here, 2 out of 6 here. And then we're going to do it again. Again, without replacement, which is always, in general, just the default, unless they tell you otherwise. So red and blue. Again, when I took this path, I already selected a red, so there's 1 less red. So 3 out of 6. I still have all my blues. 3 out of 5, by the way. 3 out of 5. I caught that. Right, yep. Also have 1 less marble in total. So this will be 2 out of 5. It's a 5. Let's make it any better. Just keep on making it darker. And down here, red and blue. Right, again, now this time you selected a blue, so there's only 1 blue left, and there's only 5 left because you took one of them out, as I learned over there the hard way. Over here, right, you didn't select, so there's still only 5 total. You didn't select the red, so all the reds are still there. Or if you just look at these two, you know they should add up to 1, so 4 out of 5. Now, before I do that, before I move on, let's talk about this again, right? X is the number of reds you could get. So look at the way you could look at your options. You could get red, red, so you could get 2 reds. You could get red, blue, or blue, red. So you could get one red, right? Red, blue is only one. Blue, red's also only one. Just a lot of odds. Or you could get blue, blue. No red. Right, so it'll be red, red. This will be red, blue, or blue, red. This is be blue, blue. That's what your X is. X is how many of those could you get, right? How many reds could you get? 0, 1, or 2. 0, 1, or 0, 1, 2, or 3. And then if I want to find probability of each one, we know how to do that. Probability of getting 2 would just be multiplying the red times the red. 4, 6 times 3/5. 12 out of 30. Multiplying again this one, now there's 2 ways to get it, right? There's red, blue, or blue, red. So you have to add them up. Red, blue, or should I say blue, red, plus red, blue. So blue, red, 2, 6, 4/5. Red, blue would be 4, 6, 2/5. So I get 8 out of 30, plus 8 out of 30, 16 out of 30. Now over here on blue, blue, instead of finding it out, I'm going to use a complement, right? Look what I have so far. I have 20 out of 30 total so far. So what's left over for blue, blue? 2 out of 30, right? The only thing that's left over. So getting 2 red, the odds are 12 out of 30. Getting 1 red, 16 out of 30. And getting blue, blue, only 2 out of 30. You also find out by doing blue and blue, 2, 6 times 1/5. So there's my probabilities. If you want to draw a little spike graph, we can. Right, I could get 0, 1, or 2 reds. 0 is at 2 out of 30, so something small like this. 1 is 16 out of 30, so something a lot higher. And then 12 out of 30 is not close to, but not totally. That's my little spike graph. I should put the y values, but